All right, so tonight we're going to take a look at Module 1, Transients. I'm going to try for us to finish this module up by the end of tonight so that we don't have any issues finishing other topics. So I'm going to be quite quick with this. Right, so transients, so in order to understand transients, we need to know what transient theory is. So if we take a look at the definition of what a transient is, you guys will see a transient is the time period during which a known voltage or current will change from an existing value to a new value due to change in circuit parameters. And that transient also describes how that change occurs. Right, so that will be due to, so that would be either due to a change in input to your circuit or a change, like in this case, circuit parameters, like let's say a resistor gets removed or an inductor gets added. So things of that nature. Right, and so once that time interval is lapsed, we usually then say the circuit or network is at steady state. So yeah, so it's going to take some time for the circuit to adjust to the new circuit conditions. And yeah, so as already mentioned, that time that it takes the circuit to adjust to it, to the new circuit conditions, that is your transient response. And yeah, so the curves, you can actually measure a transient. So it's going to be measured as a change in voltage or change in current. And depending on what, how your circuit parameters changed or what components you have in your circuit, that's going to give you a transient curve that's then associated with your circuit and its parameters. All right. And if we take a look at transient curves, they are typically then going to follow exponential laws. So if you guys just maybe do a little bit of a recap here of N5. So for instance, if you think about a capacitor charging, the voltage essentially is going to charge at an exponential rate. Same with current. So this is also, so again, we're going to take a look at RC and RL circuits for this chapter as well. Right, so we will get back to this set of curves in a little bit. This basically demonstrates different transient responses with different damping factors. But like I said, we will get back to this at some point. In fact, when we do RLC circuits, this kind of, these curves are going to get important. Right. Yeah, so the first circuit that we'll take a look at is the RC RC circuit, where the circuit is set up for the capacitor to charge. Now, our initial conditions, our switch is open, so essentially we have zero voltage applied to the capacitor. But at t equals 0, we close the switch. So if we take the voltage across the capacitor, you guys will see that it will be 0. And as time passes, the voltage across the capacitor will increase. All right, so it will follow an exponential curve as such. But at the same time, if we take a look at the current through the resistor here, or through the circuit, now the current across the resistor as well as the voltage across the resistor will follow the same trend. Right, so they both will start out at a maximum value, which will be your supply voltage in this case, and that will then decrease over time. So the current will, through the circuit will decrease towards 0 after a while. Right, so you guys will see again, this will decrease at the same rate as the voltage across the capacitor will increase. Okay, and then we get to, so then there's also the rate of change of the capacitor voltage. So this rate of change that we have here is actually where t is equal to 0, this formula. So at this point here, that's essentially your maximum rate of change. So you're basically measuring the gradient of the line there at t equals 0. So obviously that gradient is then going to get less and less steep as the capacitor charges. So then your rate of charge decreases over time as well. But yeah, so the next thing that we'll take a look at is the time constant, which is also very important in basically how quickly we charge or discharge a capacitor. Right, so if we take a look at the time constant is typically defined as the time taken for your capacitor to charge um, to 63.2% of the maximum supply voltage. Or yeah, so I think on this drawing on this graph, it's rounded to 63% of the supply voltage. So yeah, so you guys will see that is in time, that is your one time constant. Right, and then each time constant essentially, yeah, so each time constant is essentially the difference, well, you charge up 63.2% of the difference in voltage from between your supply voltage and your capacitor voltage. So yeah, so there is your difference in voltage, and yeah, so that second time constant is then going to charge up to 63.2% of that difference, and then for the third time constant, that's at 63.2% of that difference, and so on. But you guys don't really have to like fret too much over that. I'm just trying to explain here essentially what's happening. So in any case, the time constant for an RC circuit we can define as the um, product of the resistance and capacitance, and that will give you an answer in seconds. Right, and then just going further on some transient theory, let me just get a different color here. So the time that it takes the capacitor to charge to 98% of the supply voltage, that time taken is approximately 4 time constants. So you guys can see that here on the graph as well. Let me just clean up a little bit here. At 4 time constants, you guys will see we are at more or less 98% of the supply voltage there that the capacitor is charged to. And then we assume the capacitor to be fully charged after 5 time constants. Right. Yeah, so that's some definitions of little theoretical factoids you guys can try and remember, particularly the 4 time constants and 5 time constants bits there, because you can sometimes get questions in an exam or test that can ask you, okay, how long will it take this capacitor to charge completely? And you might be given the resistor and capacitor values. Then essentially you just need to go calculate what the time constant is. And once you calculated that, multiplying that by 5 will then tell you, okay, cool, that's how long it will take for your capacitor to fully charge. Right, so these are still kind of, how can I say, rule of thumb values that you guys can work with. But now, the other question is, but how do we get the other values here in between? So we can actually work that with equations. So we can actually express the voltages and currents as equations. Right. Okay, so first up, if we take a look at the capacitor voltage, so it will be demonstrated, or rather described by the equation given here. So that is going to look something like this. So that's your voltage. And then if we take a look at the resistor voltage, it will be described with that formula or the equation there. Remember, time constant is described by the value of your resistance and capacitance. So yeah, so remember, this is basically an equation or time-based equation. So this basically describes this whole curve. So remember, tau is going to be a fixed value. Everything else is going to be a fixed value except for t, your time. And of course, VC and VR, that's also going to change with time. Right, current, the same thing. So current and resistor voltage will follow essentially the same curve, essentially decreasing at the same rate. And yeah, so the textbook has a little bit of a weird phrasing of things. So they say that if there was no resistance in the circuit, the capacitor charges fully in one time constant. Now, the time constant is defined by resistance, so I don't know why they would say this, but is in the syllabus, so I guess you guys need to know that. So I think more accurately would be it would charge fully in one time constant based on the resistance of the capacitor. So real capacitors actually have a small amount of resistance. So yeah, or small amount of parasitic resistance. So there is going to be a little bit of a time constant. But as you guys can also see, just want to mention this real quick. With the time constant, you can actually increase the length of this time constant by either increasing your resistance or capacitance. And if you want to shorten it, you obviously then decrease the resistance or decrease the capacitance. Usually, it's easier to increase or decrease your resistance than it is your capacitance. You can always use an adjustable resistor like a potentiometer, whereby with the capacitor getting small enough adjustable capacitors, I don't think is really an option. Usually, your adjustable capacitors are of air, what they call air. What would you call it? Air dielectric. So yeah, so they don't make use of things like polymers or ceramic as their dielectrics. But anyways, easier to adjust the resistance, to adjust your time constant. And again, at any time instant, the sum of capacitor voltage and resistor voltage will equal your supply voltage. So if we take a look at, let's say, two time constants here, so we have the voltage across the resistor right there, and then two time constants, the voltage across the capacitor that's there. So you basically, the baby little voltage there that we lose is sitting across the resistor. So if you add these two voltages at any time instant, that will give you your supply voltage. And then obviously there's your initial conditions. So T equals 0. Your capacitor voltage is going to be equal to 0. Resistor voltage at T equals 0 is going to be the maximum supply voltage. And current is also going to be a maximum at this point. Right, then you can also go and calculate the charge stored in the capacitor. That's going to be your capacitance times your voltage. And yeah, so you can actually calculate the charge stored in your capacitor at any time instant. So essentially what you're going to do is you can just go calculate the voltage across your capacitor at a specific time. And you can then calculate the amount of charge stored. And you can do essentially the same thing with energy stored as well. So for a fully charged capacitor, your energy stored will obviously then be the capacitance multiplied by the supply voltage squared, and that whole thing divided by 2. But if you want to do it at a different time instance, of course, you will have to go and calculate the voltage at a specific time instance, and then you can go and calculate the energy stored in your capacitor for that time. Right, discharging. So in the case of discharging, I'm not going to go through everything again. So essentially the time constant definitions still apply here, except now you're not charging, you're discharging. So the voltage across the capacitor is going to decrease over time, like we can see here in the graph. Maybe switch over to red. So yeah, voltage decreases. And yeah, so if I can just quickly refer to the circuit diagram that we have here. So we essentially now have removed the source and we have a fully charged capacitor. So now if we close the switch here, now our capacitor is going to act as the source. But what is not shown here is that we're still actually measuring the positive terminal of our multimeter, if you will, or of our voltmeter as such across the resistor. And then what's going to happen is the capacitor is now going to discharge through the resistor. So the capacitor is now going to act as a battery. And yeah, so basically your current direction changes. So this is demonstrated here in the graph. So you guys will see the current here is negative. And it's going to be, again, it's going to start out as a maximum value. And that's then going to decrease towards 0 as the capacitor is discharging. Right. Yeah, so that also means the voltage across your resistor is also going to be also going to change in polarity. So this is also your resistor voltage. And for a discharging circuit, I think I'm going to no. So for a discharging circuit, at any point in time, the capacitor voltage plus the resistor voltage is going to equal 0. Right. For this particular case, yeah. There is a case that it's going to be different, but essentially what's going to happen there is you just going to swap out sources. I hope we will be able to do an example. We don't really have that much time for this. Right. Okay. So for discharging, so obviously because the curves are now different, our equations for the voltage is also going to be different. So there's your capacitor voltage, which is going to follow a curve as such. Then you have your resistor voltage. So take note of the negative there to indicate that you have a change in polarity. So again, that's going to start out negative and decrease towards 0. And you're going to have a similar thing happening with the current as well. Right, so again, just take note of the negative sign there to account for the change in polarity. Okay, before we move on to RL circuits, you know what, I think I might do an example with you guys real quick, even if we don't get enough time to get through everything. I don't think this chapter is too difficult. I think some of you guys might have had industrials in 5 with me previous term. So yeah, okay, but anyways, let's continue. So I'm just going to quickly just jump to the textbook for a moment. Okay, let's just see here. Right, okay. Just want something to demonstrate something basic first. Let's take a look at example 1.1. So yeah, so this is actually quite a basic example. So we're given an RC series network, so resistor and capacitor in series, and the resistor has a resistance of 100 kilo ohms, and the capacitor has a capacitance of 10 microfarad. And yeah, so these two components are then connected across a 10 volt DC source. Right, so there are a few things that we need to go and calculate. First off, yeah, and we're also told to plot the curves for 5 time constants for each of the following. So let's take a look. So the first thing that we need to go check is the voltage across the capacitor, voltage across the resistor. So this is actually more for the plot curves. Then the charging current as well. And now the other things, we want the energy stored in a fully charged capacitor, the charge on the fully charged capacitor, and the rate of change of the capacitor voltage. Now this rate of change, I suspect we'll see that now. It's actually the first time I'm working through this example, but I suspect this is going to be the maximum rate of change at t equals 0. Okay. All right, so if we take a look at the solution, so first off, the very first thing that you can go and calculate is the time constant. You have the resistance value, you have the capacitance value, and then for this particular example, we get 1 second time constant. And we can also go and calculate our maximum current, which is just going to be the supply voltage divided by the resistance. And this is actually quite a small current, so it's 100 microamps or 0.1 milliamps. Then yeah, so this is a interesting approach that they take here to draw the curve. It's almost want to say a grade 9, grade 10 type of way of doing functions. But in any case, so so they do the voltage at 0. That's obviously going to be 0 volts. Capacitor voltage at time constant 1, which is 6.321 volts. Voltage at time constant 2, time constant 3, and so on. So you can then use these values, so for at each time constant point, to go and draw your curve that will look something like this. Right. Okay, so pretty straightforward. So this is pretty much what we've been doing up until now. Then the resistor voltage, the textbook follows the same procedure as with the capacitor voltage, but it will look something like this. And then same thing with the current. And you can draw its curve as such. And then, yeah, so then we can also take a look at the energy stored on a fully charged capacitor. There, that's what we have here. Yeah, so the textbook actually makes use of the very precise values that you calculate, but you can use the supply voltage. Yeah, I'm going to lose it with this textbook doing this every time. In any case, as it doing this anyway, so you will get your energy stored, charge stored, and I'm going to check something here. I think they might have made a mistake here. Yeah, I think the textbook has a mistake in it. Is that there? That needs to be your voltage, which is 9.9326, and not 99.326, which is your Coulomb value. So yeah, so there's a typo in the textbook with regards to calculating the energy stored. So that answer there, I don't think would be correct. And then number 6, we want the initial rate of change. So they do use the incorrect symbol here. That needs to be dV over dt. So yeah, that's then your supply voltage divided by tau, and that's 10 volts per second. Yeah, so also the rate of change is going to be a per second, voltage per second or current per second value. Yeah, okay, this textbook, or rather Prolego, it's not a very stable site, I see. Anyways, let's continue. I think we've also done now, let me just see, because I actually want us to take a look at one of these examples as well. So this is essentially an example where the capacitor is charged and then discharged. So this is kind of an intro to periodic charge and discharge. So if we take a look, I'm just going to continue through here. So yeah, so essentially from what I can gather with this example, so they let the capacitor charge fully and then discharge. So you're going to get a curve that's going to look something like this. So you're going to have the capacitor initially charging, and then once you short circuit out the once you short the circuit so that the capacitor can discharge through the resistance, then you get your discharge curves. All right. And so here's another example, another typical example. I just want to see here. Okay, so they tell you here the capacitor has initially been charged to a value of 500 volts. When it's discharged through a 100 mega ohm resistor to a value of 100 volts. Right, so first off, time constant, very important to get that first if you can. In this case, it's 2000 seconds, so it's actually a very slow discharge rate. And if we take a look at the capacitor voltage, so we want our final voltage to be 100 volts, so that's that there. But our capacitor is fully charged or has been charged up to 500 volts. And yeah, so we need to go, yeah, so there is a bit of a problem here. That 2000 needs to be part of the exponent. That's not going to work very nicely there. But I do see that the arithmetic is correct. So you end up with something like this. So in order to get rid of the e to the power of minus t over tau, you have to take the natural logarithm and then end up with 3,218, round it maybe to 3,219 seconds, and that's more or less 53 minutes of charge time. right, so there is another question. So you guys can go through the examples. I'm not going to, if we take a look at, so this is actually what I want to get to is basically square wave inputs to your RC circuit. So this is more or less what it's going to look like. So if you have something like this, so your square wave is not necessarily going to be, your pulses from your square wave is not necessarily going to be long enough to to be one time constant long, right? So your capacitor is not necessarily going to charge completely for that pulse. And the same goes for when your square wave pulse is either zero or negative. It's not going to be at that value for long enough for your capacitor to necessarily discharge completely. So your capacitor might just discharge partially. So it will eventually get to a point where it will be fully charged, and then so you're essentially going to have what I would like to call an AC transient. Right, so you are going to get to a point where the charge and discharge curve of your capacitor is going to oscillate around an average value once it reaches a steady state. And again, that's going to take 5 time constants or 5 cycles for that to be achieved. And then we jump to the examples because per Lego sometimes be a bit fussy. Anyway, so the same thing with the current. You guys will see a similar thing happening there as well. So the current here in this case is eventually, or rather the average current is going to decrease towards zero eventually, but you're still going to get negative and positive fluctuation. All right, so 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 the textbook has a bit of a weird way of working with this. So there's the discharge cycle, and they include the initial capacitor voltage there. So that's one way of doing it. So they actually give you the formulas at each and every point. I used to do this in a little bit more of a different way with my students in the previous with the previous syllabus. So so this VR3 is basically what we're working with here. Right. Are we? Something? I'm pretty sure there's something not completely right with these formulas though. VC3, yeah, that would be then VC2, yeah, no, that would be fine. All right, so we can actually, I think we can actually do this dual source. I'll do this as an example because it's very similar to how you would work with, how can I say, very, very similar as to with the square waves that you would do the same here. In fact, I actually want us to do a square wave. I think this will actually work, but I see the one as negative, one is positive. You can also get one with both negative and positive values. There is actually an example in the textbook on that. If we, I think with, I will start maybe with an example in the next class, but let's continue. Sorry for that disconnection issue there. Anyways, okay, so if we take a look at an inductor, so we have a very similar situation as what we had with the capacitor. So first off with the inductor, again, we have a switch here, we have a source, resistance series with the inductor. So if we close the switch here, now an inductor is pretty much going to be the opposite of a capacitor in terms of its behavior when it comes to current and voltage. So the inductor is going to resist change in current essentially. So the current in the beginning is going to be a minimum or zero. So you guys will see the current will follow this curve here. And the current will increase over time. But the voltage you guys will see, because it's an open circuit at the start, the current or the voltage will be a maximum across the inductor, and this will then decrease towards zero as the current increases to a maximum value. So the time constant for an inductor just going to be the inductance divided by the resistance. So essentially the same rules we had with the capacitor is applicable here as well. So for both time constant, the time it takes for the circuit to be fully charged or fully energized rather, um, inductor can't store charge. It stores energy in the form of a magnetic field. Again, we're also going to have formulas or equations for each voltage. So for the inductor voltage, essentially going to have that. So that's going to start out at the maximum and decrease towards zero. The resistor voltage is then going to be described with this formula here. So you guys will see this equation is very similar to that of the capacitor voltage that we had with the RC circuit. So the resistor voltage is then going to increase over time there. And current is going to follow essentially the same curve. And your maximum current is then going to be the supply voltage divided by the resistance. And yeah, so there are some factors that will influence your inductance, number of turns in your inductor, cross-sectional area of your core, permeability, and the ability of your inductor to conduct magnetic flux, and the length of your conductor from which your inductor is made of. Right, so that all is going to influence your inductance, and that would be characteristics of the component itself. But in any case, we can do the inductance as the number of turns times the flux divided by the current. So yeah, so this is essentially what's used to derive the energy stored in the inductor. And yeah, so you guys also get a similar formula here as what we had with the capacitor. Only difference being is inductance and, well, the inductance obviously equivalent to the capacitance, but here we use the current instead of the voltage. All right, so again, same rules in terms of, or same definitions in terms of time constant here. Yeah, and also again, at any time instance, the sum of the inductor and resistor voltage will give you a supply voltage, and then you're going to have your initial conditions at t equals 0. Resistor across your voltage across your resistor is going to be 0, and the voltage across your inductor is going to be your maximum supply voltage, and current is going to be 0. Right, so if we take a look at the rate of change of current, in fact, yeah, I think you guys can ignore this. It's not needed for you guys to know that part. It's essentially just using differential equations to derive the, basically derive the formulas or the equations that we have here. Oh, no, not these. But in any case, so yeah, so you guys don't need to know that. So yeah, so that's something I will remove from the slide at some point. Any case, but rate of change, again, this is at t equals 0, so keep that in mind. But yeah, so in fact, actually with the RC circuit, you can actually derive the equation for any instance in time. This is just at t equals 0. So if you take, let me just quickly go back here for rate of change. So I'm just going to show you guys how to get it. So if you take, let's take for instance the rate of change of voltage across the resistor. That's actually going to give you a negative rate of change there. Oh no, it's going to give positive. Actually, this one is going to give you a negative. Let's take that one just so you guys can see. So dVL dt. So you're basically going to differentiate that, and according to the differentiation rules, this is still just going to be Vs times e to the power of minus t over tau. But I'm going to use the chain rule to then differentiate that part, which is then minus, what is this? This is going to be minus 1 over tau. Right, so yeah, so if you were to integrate this, you need to get back to where you started, right? So that's pretty much what we have here. And if I now take, simplify this a little bit, you get Vs over tau negative multiplied by e to the minus t over tau. Now, if you do if you want the maximum rate of change, t equals 0. So if you make t equals 0 here, that will then equal minus Vs over tau. And this is now specifically the rate of change of inductor voltage, right? Okay, but using the general formula there we have here, you can actually go and calculate the rate of change at any point in time, right? But it's rarely asked, so it's actually why I do not spend too much time on that. In fact, usually they ask for the maximum rate of change. I haven't really seen in a question paper where they ask it at a different point in time. But anyways, just to be a little bit thorough there. Right, so again, you can also discharge an RL circuit. So the same principles apply as what we had with the RC circuit. Again, this is what our formulas will look like, for our equations. So discharge, or rather the voltage across your resistor, will now be a maximum. But something that's a little bit different on this circuit though. So let me maybe quickly go to our equivalent circuit. Yeah, this is the one I'm looking for. So if I now short out, let's say I short out, so at the point when the inductor voltage has reached the 0, we now short this out. Now, essentially what's going to happen is the inductor is going to want to continue. So this is now all like Lenz's law and Faraday's laws at play here. So the inductor is essentially going to want to continue to push current in the same direction. And that's why current, so you guys will see when during the so-called discharge cycle, the inductor's current is not going to go negative. It's going to flow in the same direction. But what is going to change, however, is the polarity of the voltage across the inductor. So your inductor voltage is going to change, right? So in order to keep the current, to keep pushing the current in the same direction. So that's why the voltage, you guys will see, the voltage will actually also change polarity on the inductor, while the voltage across the resistor now, so the voltage across the resistor is now going to be the same as the voltage across the inductor, because these are the two only components in the circuit now. And the inductor is acting as your source. So if we go back to where we were, so again, see the resistor voltage, that will be positive because the current is still flowing in the same direction. So the current didn't change direction. So the resistor voltage will stay positive, but it's going to start at a maximum and decrease towards 0. The inductor voltage, on the other hand, that's going to be, so the voltage on your inductor flipped polarity. So of course, that's going to then show as such. That's also going to decrease towards 0. And now for this discharge circuit, at any point in time, the sum of voltages need to be equal to 0. And if we take a look at the current, that's going to follow the same trend as the resistor voltage. Right, so again, time constant still the same that we calculate with L over R as we had with the charging circuit or energizing circuit. And maximum current, again, that's going to be our source voltage divided by the resistance. Yeah, all right, so that was RL circuits. Then we get to RLC circuits. So I'm not going to, I see we don't really have that much time. So I think I might with the next class go into do this and go into transducers as well. We'll try. But there is a strong possibility that you guys might have to do some self-study on some of the on one or two of the modules. I'm going to see if we can maybe do the theoretical modules that you guys can do self-study there. Actually would like for us to do an example or two for this as well. But in any case, I'm not going to wrap up just now. I'm just going to let's just get going with RLC circuits, and then we can go from there. All right. Okay. So yeah, so we're not really going to distinguish between parallel and series here, but there is a few things that we are going to take a look at. So resonance is going to be one of the things that we need to consider here when looking at transients. Now, you guys should probably know by now, if you've done in 5 and in 4, that when you have a capacitor and an inductor in the circuit, that these two components will interact with one another in the way that they will charge and discharge each other back and forth. And in an ideal world, if one of them, let's say the capacitor in this case, so if we take a look at this situation that we have here, we have an initially fully charged capacitor that will then discharge through the inductor. Now the inductor is going to set up a voltage or what we call back EMF to counteract the voltage of the capacitor. So it's going to look essentially like that. And the current is going to flow in that direction. Once the capacitor is fully discharged, the inductor voltage, in order to basically counteract this, well, essentially your magnetic field is going to collapse, and that's then going to reverse the voltage on your inductor is actually what's happening. And then that's going to continue pushing current in that direction. And then that's going to charge your capacitor to opposite polarity, and then the cycle just restarts again in the other direction, and this then happens back and forth the whole time. Now the frequency that this back and forth charging and discharging happens is your oscillating or resonant frequency, or actually your resonant frequency. And in an ideal world, this charge and discharge will happen indefinitely. But because we live in the real world, the inductor has a little bit of a resistance on it, actually significantly higher than what a capacitor would have. You are going to have some energy losses. So essentially what you're going to get is something like this. So where your capacitor and inductor charge, discharge, and it's going to look something like this until there's no more energy left to charge and discharge. Right, and then for resonant frequency, we know we get resonance when the inductive and capacitive reactances are equal to one another. And that then leaves us with the resonant frequency formula there. Now, again, in practice, we always have some resistance in our circuit, whether it be parasitic to the inductor or capacitor. Some of that stored energy is then dissipated in the form of heat, usually during each charge and discharge cycle. And that means that the amplitude of each exchange or oscillation is going to decrease with each cycle, each half cycle, until we don't have any more oscillations. And then we get to what we call the natural frequency of oscillation for an RLC circuit, which is very similar to your resonant frequency, but not completely, because the oscillations do die out on this. So you then get a formula that will look something like this. It is very similar to your resonance formula, but your natural frequency will also be less than your resonant frequency. All right, so I think this is a good place to end it, because this thing now is going to tie into damping, or well, critically damped, overdamped, and underdamped systems. So yeah, so you guys can actually maybe go and think of a few examples of critically damped systems, overdamped systems, and underdamped systems. But yeah, I'll continue with this in the next class, and then hopefully we can also wrap up chapter 2 as well. But in any case, guys, if you guys don't have any questions, have a good evening, and I'll see you guys for the next class. Cheers.